Welcome to the course of Geometry and Quantum Field Theory. This is a joint course of NTHU and CTS, and I'd like to welcome everybody. And part of the course is online. So if you have any questions, whether you are in the classroom or online, please let me know, and I welcome questions. So the course is in the interface of mathematics and physics. So it has 3 lectures every Wednesday afternoon. But due to the content of the course, so the course each afternoon, Wednesday afternoon, the lectures will be separated into 2 parts. The first part is on mathematics, and the second part is on physics. And there is a longer break in the middle, and I hope this is okay with everybody. Oh, okay. All right. Okay. All right. So let me restart. So this is a joint course of NTHU and CTS on geometry and quantum field theory. And I'd like to welcome everybody, whether you are in the classroom or online. If you have questions during lecture, please let me know wherever you are. This is a course in the interface of math and physics. So according to the content of the course, each Wednesday afternoon, we will have officially 3 lectures, but it will be separated into 2 parts. The first part will be on mathematics or more mathematics oriented, and the second part will be more physics oriented. So regarding the way, if you are officially registered, regarding the way of evaluation, there will be a few homework problem sets, but there will probably be no official exams. So let me start with some general information about 4-dimensional manifolds, since much of the course will be on that topic. And I'll start by reviewing what is known in general. So I'll start with some very elementary remarks about 2-dimensional manifolds, namely surfaces. So suppose we want to classify oriented surfaces, compact oriented surfaces without boundary. So suppose I say closed. Closed means manifolds that are compact and without boundary. So suppose we look at closed orientable surfaces. Surface means a 2 manifold. These 2 manifolds are classified easily, namely by very standard topological informations. For example, by pi 1, suppose the surface is sigma, they are classified by the fundamental group, or by the first homology group, or by the first cohomology group. So either of them would work. And it's a complete classification. And the only restriction is that, well, usually for any manifold, the cohomology H1, upper one, has no torsion. This is from the universal coefficient theorem. And then from Poincaré duality, H lower one has no torsion either. But in 2 dimensions, there is a particular restriction, that being that this H1, as I said, is a free abelian group, and it is always of even rank. This is because, again, by Poincare duality, there is a non-degenerate antisymmetric bilinear form if I take H alpha 1, then it's just given by the cup product, then pair with the fundamental class of the surface. So this implies that the rank of H1, which is denoted by the first Betti number, is even, and then half of that is called the genus of sigma. And so that's the only sort of restriction. And then surfaces are classified by genus, which could be 0, 1, 2, 3, etc. And I'm sure you know the topology of these surfaces. Now, going to 4 manifolds, things are not so simple. And one is suppose X is it's a closed orientable. Again, closed means compact and without boundary. Closed orientable 4 manifold. Then in that case, H1, if I do not write any coefficient, it means integer coefficients. So in that case, H1 can have torsion. And if so, then so do, by universal coefficient theorem, so do H upper 2 of X. And then by Poincare duality, H lower 2 of X. They may also have torsion. In fact, almost the same kind of torsion as H lower 1. But then we still have the notion of intersection form. So even if it has torsion, we could we can first of all get rid of the torsion for simplicity by taking the free part, which is this abelian group mod its torsion subgroup. So the free part is not naturally a subgroup, but it's a quotient of H2. And that's it's finitely generated because the manifold is compact and it is torsion free, and therefore this is a free abelian group. Of finite rank. And the rank is usually denoted by the second Betti number of the manifold. And there is a intersection form, just as the surfaces do, which are mentioned in a moment. So that's about H2. But on the other hand, we could also look at whether the manifold is simply connected or not. Most of those surfaces are not simply connected. But if we look at the 4 manifolds, things are very complicated in the sense that every finitely presented group, these are discrete groups which have a finite number of generators and also finite number of relations. Any such group can be the fundamental group by one of such X being described before. So that is a lot of possibilities. And unfortunately, there is no algorithm to decide whether two finitely presented groups are isomorphic or not. So this is a question of sort of undecidability in computation. And usually in the theory of four manifolds, at least according to the present status, we are only going to be concerned with simply connected four manifolds. Now, for which is already a very rich story. So for simply connected four manifolds X, what we have is that its abelianization, namely H lower one, is zero. So the first Betti number is zero, and also because H lower one is zero, we have H upper two and H lower two as well by Poincare duality. They have no torsion. So this is a case that we will be concerned with for the most of the semester. So these are rather preliminary remarks. Are there questions? So if not, then we will get to the more precise details. Now, I'm going to first talk about the four-dimensional analog of the intersection form. So again, let X be a closed oriented, because I do want an orientation form manifold. And I'm not assuming for the moment that the space is simply connected. Now, even in this generality, we can have the intersection form. Of the form manifold X is the bilinear form, which I will always denote by eta of X. This bilinear form is defined on. So the bilinear form is on the second cohomology of X, and it's given by so eta of X of small x and y is equal to. So I'm first going to say where small x and y are located. So there are second cohomology elements of the manifold, and so the definition is that it's you first take the cup product and then pair with the fundamental class of X, since X is already oriented, so you do have a fundamental class. So this is one version of intersection form. As I said, when we do not assume that X is simply connected, H upper 2 can have torsion, and fortunately, these are integer valued. So maybe I should say that these are integer valued. And once you realize that whenever X and Y whenever x or y is a torsion element, then the value is 0. Therefore, the intersection form descend to the free part of the second cohomology group, namely, which I explained earlier, that is a free abelian group of finite rank, which we call a lattice. So this is the notion, and there are also other very simple concepts associated to that. These are so we have already B2, the second Betti number here. We also have now we can separate it into two parts. So B2 plus and B2 minus. These are the the dimension of the maximal linear subspaces. In a vector space, which is H2 of X tensor with real numbers, so these are real vector spaces, and the quadratic form eta extends linearly, real linearly, to this vector space, and there's a maximal dimension of subspaces on which eta x is either positive or negative, definite, and these dimensions are called B2 plus and B2 minus, and then finally we define the signature of the form manifold, and this is defined by sigma x equal to B2 plus minus B2 minus, and that's the standard signature for a quadratic form. Now, I want to erase something. So let me make a few simple remarks about this intersection form. Now, first of all, by Poincaré duality, this intersection form on so once we descend it to the free part is non-degenerate. This follows very simply because the pairing of cohomology and homology is non-degenerate by itself, and then together with Poincaré duality, you see that very clearly. And moreover, unlike the two-dimensional situation for which the intersection form is on H1, now the intersection form is on H2. 2 is half of 4, and 2 is still an even number. So, so this intersection form is symmetric. Now, then the second remark would be something about how intersection forms are related when we look at new form manifolds constructed from the old ones. So if X bar is the same manifold with, as X, but with the opposite orientation. Then the fundamental class has a minus sign in this definition. So the fundamental class of X bar would be minus of that of X. So the intersection form also takes a minus sign. So that's very easy. And finally, if X prime is another such means these conditions in the definitions are satisfied. So if X prime is another such four manifold, then we can, I should have said that earlier, once you realize this, then B2 plus is exchanged with B2 minus, so the signature also is reversed. So now finally, if X prime is another such four manifold, then we can form what is called the connected sum. So, so the connected sum is a simple procedure in topology. So you take away a solid, in this case, a solid four-ball in both manifolds, and the boundary would be S3, and then you glue two manifolds to form, and then you smooth the corners to form another four manifold. So this is the connected sum. It's very easy, for example, by Mayer-Victoris, to show that H to actually behave by a direct sum, and then you look at H2, and then there's the new manifold has an intersection form. So this lattice with this non-degenerate bilinear form is actually isomorphic to the direct sum of two lattices. So the H2 part are already discussed. But why the intersection form also is a direct sum? This also follows from a simple consideration in topology, which I leave as an exercise. And subsequently, then consequently, we can have B2 plus or minus of the connected sum is equal to the sum of the two. And also the signature behave additively. So these are some simple remarks about the intersection form. Are there questions so far? Are there online questions? Okay. This is simple enough. So let me first of all give some simple examples. I will come up with more slightly complicated examples when we study all the possible intersection forms of four manifold. But first of all, let us start with the very elementary one. So the first example is most trivial, and that is the four sphere. And the four sphere has a 0-second cohomology group, and therefore any form on it has to be 0. And the second case is the first slightly non-trivial case, and that H2 that's the projective complex projective space, complex dimension 2, and H2 is a copy of that, and so if you remember your exercise in algebraic topology, the generator, if you take the cup, it's the generator of H4 paired with fundamental class, that's 1. So this eta x is, in terms of matrix, it's 1, and it's a 1 by 1 matrix. So that's easy. So you have, so in other words, B2 is equal to 1, and that's equal to B2 plus, and B2 minus is equal to 0, and sigma is equal to 1. So the third example is we are going with a high rank of H2, and in this case H2 is Z plus Z, and the intersection form is this matrix. So this is a 2 by 2 matrix, because you know the cohomology of the two-sphere, and then it's easy to take the cup product. So it's they are indeed symmetric matrices with integer entries. So B2 of x is equal to 2, and B2 both plus and minus is equal to, they are equal to 1, and sigma is equal to 0. So the last example, which is still elementary, is that x now, as I said, if we have a few 4 manifolds, we can take the connected sum. So if I take p copies of, so how do I denote that? So p copies of the connected sum this way, p copies of connected sum of CP2, and then connected sum with q copies of CP2, but with opposite orientation. You see, CP2 is a complex manifold, so the complex structure gives an orientation. But we can, as a smooth manifold, it can have the opposite orientation, and I'm doing that now. So P and Q are integers, and they are now negative, and to be interesting, at least one of them should be positive. And in this case, because of the earlier remarks, so we have h of x is the direct sum of p plus q copies of z, and eta x is given by the matrix. So there are p plus ones and q minus ones. And then you see clearly that B2 plus is P plus Q, B2 plus, sorry, B2 is P plus Q, B2 plus is P, B2 minus is Q, and the signature is P minus Q. So those are then very simple examples. So are there questions? So So, 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 remark, which is a bit beyond the first semester course on algebraic topology, even in the version that I taught it. So this will involve characteristic classes that I covered in my second semester topology here. So for those of you who know characteristic class, I'm going to make some remarks. For those of you who don't know, you can just ignore this. This is because I'm going to explain why characteristic classes are not so helpful for getting information of four manifolds. So for finite manifolds, we do have a topological invariant, which is H2 with its intersection form. But I'm going to show you that for a while, this is the only information that we have, unless we want to use some very advanced tools in geometric analysis. So, of course, if you know enough topology, you know that cohomology groups or even homotopy groups are not everything about a space in classical topology. There are also characteristic classes of vector bundles. And on manifolds, especially on smooth manifolds, there are natural vector bundles, such as the tangent bundle or or the algebraic constructions that can derive from the tangent bundle. And these characteristic classes are useful in many ways. And I'm going to explain that for four manifold, it's not going to give us a lot of information. So characteristic classes are of vector bundles, which can be real or complex. And first of all, our manifolds are real manifolds. So let us look at real vector bundles. So first of all, let X be a closed oriented or orientable. Now, because I want to consider tangent bundle, so let's say that it is a smooth four manifold. Then what we have is that we can have natural vector bundles over the manifold, and the first, well, actually, virtually the only vector bundles is tangent bundle or some vector bundles that can be directly constructed from it algebraically. So we have characteristic classes. Now, characteristic classes of the tangent bundle so we want to say that they do not provide more information than the intersection form, let's say. So what are the characteristic classes? Well, when we have the Stiefel-Whitney class. So the first W1 is equal to 0. This is because we assume that X is orientable. Now, in the early days of topology, there was great hope for Stiefel-Whitney classes to provide more information. But in a shocking work of Wen-Qing Wu in the 1950s, he showed that Stiefel-Whitney classes are homotopy invariants. So that was very disappointing. Certainly this is a wonderful result. And in our case, actually, we can say that what the second Stiefel-Widner class does. So W2 of X is in fact determined by the mod 2 version of the intersection form in the following way. So there's Wu's formula, which says that, well, if you look at, let's say, any element in the second cohomology with Z2 coefficient, then the pairing of A with itself is equal to the pairing with the second Stiefel-Widner class. So and these are in Z2. So that means since the mod 2 intersection form is also non-degenerate because there's a mod 2 Poincaré duality. So you see that W2 is uniquely fixed in this way by the information of the intersection form, and therefore it has whatever that comes from W2 can come from the intersection form. And if you are not fully convinced, we can do an explicit calculation. To show that W2 is not so interesting in terms of giving extra information of four manifold. So if sigma is an embedded surface, then this actually provides information about the second homology. So if you do this mod 2 fundamental class of sigma, and then you pair that so with the second Stiefel-Widner class, if you can compute it explicitly by classical information in topology, then it means it doesn't give new information. So in fact, this is a rather easy computation. So if you restrict your tangent boundary of the four manifold to the embedded surface, then this is certainly the tangent boundary of the surface plus the normal boundary of the surface and Stiefel-Widner class head in this case. So this is W2 of sigma plus W2 of the normal boundary of sigma and pair with the fundamental class. An easy calculation shows that this is actually, the first one is actually, because for surface, W3 is already the top, so it's the Euler number, and the other is the intersection number of sigma and sigma, and again, we are in the mod 2 case. So you see, indeed, you see that this is completely standard information. So this is another way to see that W2 doesn't give much fancy information. And the last, so maybe I should erase that because this is just an explanation. So the last two possibilities are in the fourth homology. So if we look at the Euler class of the tangent boundary and then pair with the fundamental class of it, this is just so the Euler characteristic of X, and again, this is completely standard classical information. And the other thing is that if we look at the first Pontryagin class of X or Tx, there is what is called the the Hirzebruch signature theorem. And which I also covered at the end of my second semester topology. And that is 3 times the signature of X. And again, that is also completely given by the intersection form. So, so what I said is there's nothing new other than the intersection form if I consider more fancy things. So this is about real bundle, but what about complex vector bundle? Well, X started. It starts with a real manifold X, but sometimes X can have a complex structure, and the existence of complex structure is always a problem beyond topology because it involves integrability. What is completely within topology is the existence of almost complex structures. An almost complex structure is not necessarily integrable, but nevertheless it gives a complex structure on the tangent bundle, and therefore we can regard Tx as complex vector bundles of X. And once we do that, then there are additional characteristic classes, and there are the Chern classes. So let's remark that that if X has an almost complex structure, let's say J, then we have complex tangent bundles. So this is the holomorphic part of the tangent bundle. So this is a complex vector bundle. Complex vector bundle whose rank is equal to the dimension of the manifold. In our case, it's 4. And we have the C1 of the manifold, which is defined as C1 of this holomorphic of the tangent bundle, and that's in H2 of X with integer coefficients. And we also have C2, but C2 is just equal to the Euler class. So we already said that the Euler class is not so interesting in terms of intersection pairings. So we are mainly concerned with C1. Now, what it turns out is that both the existence of almost complex structure and its C1. This C1 is C1 with this fixed J. Both the existence of J and C1, they are also completely determined by the information of the intersection form. So this is so I quote a result and then explain roughly how to get it. So so there's the fact is that the almost complex structure exists. There's a necessary and sufficient condition, and the condition is that there exists a C in H2 of X satisfying the following equality, which is eta CC, is the intersection pairing of C with itself, is equal to 2 times the Euler number plus 3 times the signature. Now, if so, if that exists, then C1 of X with that almost complex structure is precisely C. So you see, again, everything is given by, all the information is given by the intersection form. And moreover, there's another condition. Maybe I'll erase that. So this equality holds, and also this C is a lift of is a lift of the second Stiffer-Witten class in the Z2 cohomology. And if this is the case, then C1 is actually that precise C. So if we take this J given in this way. So the way to derive this equality is an exercise in characteristic classes, because you have a vector bundle. If you forget the complex structure, then it becomes a real vector bundle, and that real vector bundle is precisely T of X. And therefore, the Chern classes of the complex vector bundle are related to the Pontryagin classes of the real vector bundle. In particular, C1 square is related to C2 and P1. C2 is the Euler class, so it gives this term. P1 gives the signature. So that's how this formula is derived. But then this shows it shows that everything is determined by the intersection form. So there's also, you do more exercise, you can show that in this case, namely if if and only if conditions actually hold, then B1 of X plus B2 plus of X is odd. There's also a converse. So of this if. So conversely, if either X is simply connected, or the intersection form is indefinite, it's not positive or negative definite, so it's indefinite. If B1 of X plus B2 of X is odd, and then there is C and eventually J exist. By C and J, I mean those satisfying the previously mentioned conditions. So again, everything is determined by the intersection. Everything that we can think of, if we stay within the framework of traditional topology, is determined by the intersection form. Other questions? Yeah. Well, if you require integrability, then it's a very complicated question. But if your question is about almost complex structure, then it says that because you can always deform almost complex structure, so it's highly non-unique. But you can talk about homotopy classes of almost complex structures. And the statement actually implicitly says that there's a one-to-one correspondence between C satisfying these conditions and the homotopy class of J. Yeah, thanks for the question. Are there other questions? Right. So you mean this converse, right? Oh, right. So okay. So you usually do this by obstruction theory. So a complex structure. So if you look at the vector space, right, the vector space is supposed to have already a Euclidean structure on the four-dimensional vector space. So if you look at how many complex structures there are, and you find out that the set of complex structures is an SO4 mod U2. And that's homeomorphic to a two-sphere. So an almost complex structure, without worrying about integrability condition, is actually a section of the S2 bundle over the four manifold. And to construct a section, this is not a vector bundle, so it may or may not have a section. To construct a section, you first do it on the 0 skeleton, 1 skeleton, 2 skeleton, and then 3, 4 skeleton. And then you meet with a series of obstructions. And it turns out that these obstructions are precisely vanishing if you require this condition. So that's the standard. So you may want to go to detail, but this is the rough idea. Are there other questions? All right. So how do I do with the time? So I believe, let me spend some more time in mathematics before we take a break and then shift to physics. So unless you have more questions, so are there online questions? Right. So before I give you more information on four manifolds, let us make a digression on lattices. So these are three abelian groups with certain kind of bilinear pairing on it. So before I talk about further information on four manifolds, let us be clear ourselves what are the possible intersection forms of integer lattices. So there is a classification which will be useful in the study of four manifolds. So a lattice is a finitely generated free abelian group, and its rank, which is denoted so the rank of a lattice L, which is denoted by K of L, is the rank of the abelian group. So this is about lattice. Then we talk about so a symmetric bilinear form eta on the lattice is so maybe just a symmetric bilinear form on L is a map eta from L cross L to Z. Eta of xy. So sending, let's say, sending xy to eta of xy in Z and xy are both in L, which is linear in both x and y. So then, so these are extremely simple terminologies, but I have to say it to be complete. So then this lattice with this symmetric bilinear form is called even if eta of xx is an even number. For any x in L. And otherwise, it is called odd. So these are very natural definitions. So this lattice with eta is called positive or negative definite if the linear extension of eta on so the real vector space is so. Finally, the signature of L, which is denoted by either you denote it by sigma L and eta, or simply by sigma of L if there's no confusion about eta. So is the usual signature. That means it is defined well, for four manifold in the standard way, which I erased. It is the usual signature of eta on that vector space, a real vector space. Okay. So and finally, which is very important. So this lattice with the linear form is called unimodular. If modular, if you choose if you choose Z basis, which are called EI of L, the condition is that the determinant of the symmetric matrix is equal to plus minus 1. And once this is true for one z basis, it is true for every z basis. Okay. So that's some simple definition. And I'm going to have questions. So I'm going to end up with some, again, rather elementary remarks of lattices and bilinear forms, and then we'll break and before I go to the physics part. So so the first remark is that so if L eta is a lattice with a symmetric bilinear form, then of course can reverse the bilinear form, and it has an opposite signature. So that's the same for the four manifold that we mentioned, and moreover, this minus with a minus sign is unimodular, if and only if the form without a minus sign is unimodular. Okay, so that's completely trivial. And so the second, given two such, well, what do we mean by such? Two lattices with symmetric bilinear forms, which are denoted by L eta and L prime, eta prime, then so there we define their direct sum is then denoted by this plus, and this is defined as you take the direct sum of two abelian groups and then you put together two bilinear forms in the diagonal way, and then the n-fold direct sum of the lattice itself is denoted by m times this, or simply by m of the lattice. If there's no confusion about what the symmetric bilinear form is. Okay, so finally we have so if we have two lattices, we can obviously define. So I'm not going even to write down what the definition is, because everybody knows. So we can define isomorphism. So we have two lattices with symmetric bilinear forms. So and then a lattice is called decomposable if it is isomorphic to the direct sum of two proper sublattices, and otherwise it's kind of like irreducibility. Otherwise, it's indecomposable. All right. So yeah. Okay. So are there questions? Yeah. Oh yeah. Right. Yeah. So otherwise, yeah, that's the one condition that I forgot to mention. So, this is it should be, yeah. Thank you very much. Yeah, so this is obviously it is should be symmetric. Yeah. Okay. Are there other comments? Okay. So if not, then we will take a break. And if you have for online audiences, if you have questions, you can probably let us know one way or another. And the break will, let's say it will be 15 or, and when we come back, we will look at the physics aspect of this course, and we will start with a review of electromagnetism as an abelian gauge theory. Yeah. Yeah. There are other questions. Sorry. Okay. So yeah. Thanks. Right. Yeah. Yeah. Of course. So so we can define. What I mean is I'm not going to write the precise definition of isomorphism. I'm just going to say that we can define because everybody knows what the definition is. Okay, so let's take a break. Hello. Okay. So let's start with the second part of the course, which is today. It's a review of classical electromagnetism. So this is a math course. So in physics, we start with a much more elementary level, and that is actually maybe first year, at most second year undergraduate physics. Now, in classical electromagnetism, the important quantities are the following. So E, E is it's a function of time and space. So this is the electric field, and there's also B, also a function on the space-time. This is the magnetic field. So these are the fields that are important, and then there are sources of the field. So rho, that is also a function of space and time. So this is the matter part. So this is the electric charge density, the amount of electric charge per unit volume. And then there is an electric. So they are also all functions of space and time. So there's the electric current density. So this is also per unit volume, but it has a direction because it flows in a certain direction. And then there is a constant, the speed of light, which appears in the Gauss unit or the modified Gauss unit without a factor of 4 pi. The speed of light. In elementary physics or in engineering, it may be useful to take the SI unit. But in high energy or in theoretical physics, we are best with the Gauss unit, which put the electric magnetic field in an equal footing. So then the fundamental equations of classical electromagnetism as follows. So I group them into two categories because from the geometric point of view, they are completely different. So the first category of the equations is that the curl E is equal to the minus, which is a very important minus sign, the time derivative of the magnetic field. And then the magnetic field is divergence free. So these two equations form group 1. And there are two additional equations, which the divergence of E is equal to rho, where all the notations are explained above. And then the curl of B is equal to plus dE dt, and then plus J. The last term, J, is put in by Maxwell, and this is why the whole set of equations are called Maxwell equations. But in fact, the first one is Faraday's law of electromagnetic induction. This is the non-existence of magnetic monopoles classically, and this equation is the Coulomb's law, and the last part. So this, without J, it may be related to Ampere's law, but otherwise it's the last equation. Now, so we are going to this itself. These equations, the last two equations form group 2, and those equations are already very beautiful in their own rights. And this is one of the most fundamental set of equations in classical physics. But we are going to put them in a more mathematical terminology for our subsequent analysis. And namely, I'm going to define a differential two-form on the space-time four-manifold, and to write these four equations in two very simple, very short equations. So to do so, we'll review three-dimensional calculus. So in 3 dimensions, we have the space of smooth functions, and we can take the gradient operation, and that if we take a gradient operation, we have so on any manifold, I'm going to denote the space of vector fields by curly x that manifold. So so then it is an operation from scalar field to vector field. And then I can take the curl from vector field to another vector field. And finally, if I take the divergence, I return to the space of functions. So, so these basic operations in three-dimensional calculus, and just like a complex, like the de Rham complex, if you compose two adjacent maps, you get 0. So that is sort of makes us to suspect that it is somehow related to the de Rham complex. So if you look at 0 form, and then you look at 1 form, and then you look at 2 forms, and then you look at 3 forms. There is a similar complex, except that all these operators are called the Rham differential D. And there is, of course, a relation between these horizontal lines that the first spaces are identical because 0 form is just a function. And all the other spaces are isomorphic. And I'm going to denote the isomorphisms by the degree of the differential form. By the degree of the differential form. And it's very easy to write down the isomorphism. So, for example, if I have a function here, then it maps to f times dx wedge dy wedge dz, and it is that very simple isomorphism which are called by 3. And suppose I have a vector field x1, let's say ddx plus x2 ddy plus x3 ddx3. Sorry, ddx3 should be z. We are consistent with the notations. And phi 1 is just to map this vector field into, let's say, into one form. That is very easy. x1 dx plus x2 dy plus x3 dz. Okay, so that's the easy map. And I can also map in this way. And then x1 dy wedge dz, and x2 dz wedge dx, x3 dx wedge dy. So, so these are clearly they are isomorphisms, and the point is that that this diagram commutes. So in other words, up to isomorphisms, our standard operations in vector calculus are simply the de Rham differentials. They are identified with de Rham differentials in this very simple way, and that is clearly consistent with the composition of adjacent maps being 0, because d squared is 0. Okay, so so you can check that explicitly, so I'm not going to check it. But once we have this notation, then we have that the electric field, which is a vector field, but it's not just a vector field on, it's not just a vector field on R3, it's actually dependent on the fourth variable, which is time. On the other hand, so is the magnetic field. So these two physical quantities, they are vector fields, actually form a differential two form on four-dimensional space, which I'm going to write down in a moment. And the four-dimensional space is R1 cross R3, where R1 has the time coordinate, and R3 has the standard XYZ coordinate. So this is a four-dimensional space-time. Right now, it's just a trivial product of these two spaces. But I'm going to write down the equation to rewrite these Maxwell's equations, and by doing the following way. So let's define a two form. So this two form is defined as minus, let's say, C dt wedge phi 1 of E1. So let me explain the first part. So E is, so forget about the time. E is a vector field on R3, so it defines a one form on R3. And then in the fourth dimension, you wedge it with sort of essentially dt. So that is already a two form on R4. So because so the t dependence is not just here, but this E also is t dependent. So this is again. But anyway, this is a two form on R4, and then you write down phi 2 of B, and that's a two form on R3 pull back to R4, and plus it's time dependent, so it's again dependent on the fourth variable. So this is a two form on R4 because we will later put indefinite inner product on R4. So let me write it on R1 plus 3. So this is our two form, and then using the commutativity of this diagram, and then a simple exercise shows that this is a exercise in differential geometry. So the first part of the two equations, namely these two equations, are equivalent to a simple statement that F is a closed two form. So by this D, so this DF, this D is a four-dimensional D, where those D's in the diagram are three-dimensional D. So the four-dimensional D has an additional derivative in the time direction, and that you need to take into account when you calculate df, and that leads to those sort of derivatives of the field. So that is so they are mathematically equivalent. And then to write down in a simple form the other two equations, we will need some additional information. The additional information is that in differential geometry, we can actually define what is called the Hochstar operation on differential forms. So suppose we have so mg. This is a Riemannian manifold. So of dimension and suppose it's orientable, and moreover it's oriented. So a volume form has chosen that is compatible with the orientation and also compatible with the Riemannian structure. Now, in this case, we can define what is called Hodge-Star operator. Most of you have probably already seen it. So this is from the space of p-forms to the space of n minus p forms. And it sort of just the most standard way. This is defined pointwise, the most standard way in linear algebra. So, so if I really want to write it down, so suppose we choose a coordinate frame. No, I don't want to write it down. But I'm going to write it down later in 4 dimensions. Let's first talk about its properties. So, so first of all, if you do it twice, it returns to the p form, and so this is plus minus the identity map, and the plus minus sign depends on p and n. And there's a definite way to do that. And the second, most importantly, so this is just linear algebra, but most importantly, which is also from linear algebra, is that if n is even and p is half of n, then this is kind of a self-dual situation. So the Hodge-Star maps the half degree differential forms to themselves. This operator depends only on the conformal class of the Riemannian metric. So if you scale it by a positive function, this is going to change the Hodge-Star operation on all other degrees of differential forms, but it doesn't change in the middle dimension. And now let's look at the simple situation that we are actually going to use. So if n is equal to 4, namely we are looking at 4-dimensional manifold, and p is the middle dimension, p is equal to 2, then since n and p are completely fixed, the sign is fixed. The sign here is fixed. So I'm going to tell you that in 4 dimension, in the Riemannian case, this is positive 1. So if you do it twice, it returns to itself. So here we have an involution, and then we have the 2 form on M. This is a 4 manifold. Can be broken into the positive part, or the self-dual part, and the anti-self-dual part. This is so according to eigenvalue, which could be plus minus 1 of Hodge-Star operator. So there is a decomposition. This is a decomposition of real spaces. So in this case, let me write down explicitly what the Hodge-Star is. So suppose we have, let's say, suppose we have coordinates, and we have written components of differential forms in the standard basis. differential two forms becomes antisymmetric tensors, and so the mu nu are indices that runs from 1 to 4, and this is equal to 1/2 of let's say epsilon mu nu lambda rho. Not exactly. Let's say lambda rho alpha beta yeah. So mu nu is so mu nu, and I'm going to raise. Sorry about that. So we have lambda omega alpha beta, and then I have lambda rho. Then I have G inverse, which is lambda alpha, and then G rho beta. So I believe that is correct. So that is the explicit formula for the Hodge star. When we have a 4 manifold, then the Hodge star is in the middle dimension. Now, the epsilon is the completely antisymmetric tensor, sometimes called the Levi-Civita tensor. But we're not going to look at the Riemannian case. What we are going to do is on this 4-dimensional sort of vector space, or affine space, if you want to forget the origin, we have coordinates. Now, the way Gauss unit was designed makes us very easy to fit with special relativity. So we could write x0 equal to ct, x1 is equal to x2 is equal to y, and x3 is equal to z. So these 4 coordinates are 4. And suppose we look at a metric. So this is called the Lorentz metric. And that is g is equal to minus dx0 square and plus dx1 square plus dx2 square plus dx3 square. So if we do that, if you use the same formula for the Hodge star, then you find out that Hodge star square is minus the identity on the 2 form. So this is because some of the matrix element of G is minus 1, and the inverse also retains this minus 1, and it ends up with a minus sign. And therefore, if you really want to make a decomposition of the 2 forms, you have to complexify it. So this, for example, plus would be the eigenvalue of Hodge star with eigenvalue I, and the minus space would be the eigenspace with eigenvalue minus I, etc. So you can also do that, but it involves complex linear combinations. Now, in order to be explicit, let me show you that a few calculations. So on the 2 form, if you follow this definition, then you can compute it. You find out that there's a minus sign here, and if you then do the Hodge star dx2 wedge dx3, you have dx0 wedge dx1 with no minus sign. Of course, everything is correct if you do cyclic permutations of 1, 2, 3, because at least 1, 2, 3 are symmetric. so this is about a Hodge star in 4 dimensions. Are there questions? Right. So let's with this we can now rewrite the second group of equations in the classical Maxwell's equation. So what we do is that, so I also leave you as exercise to actually verify it. So F is a 2-form, so I can compute Hodge star. So let me write down the result of the calculation. So it's the CDT. So this CDT is now dx0, right? Because of the way we define coordinates. So this is dx0 with the plus sign wedge phi1 of b, and then we have also a plus sign phi2 of e. So you see, this is a simple calculation on differential forms, but you see, this is completely wonderful because the Hodge star exchanges electric and magnetic field. Moreover, the exchange is that B goes to E, but E goes to minus B. So this is like you have a matrix S is equal to 1 minus 1 in number theory, and its square is minus 1, unless you go to the PSL2. In SL2, the square is minus 1. So this is just like, this is very much fit the statement that the Hodge star square is minus the identity. Now, Hodge star exchanges essentially electricity and magnetism, and also the second equation, the second group of equations can be written as d star f equal to something, right? And it's not equal to 0 because in the previous case we just have E and B. There's no other things, so it's not surprising that it's just E and B with some operation is equal to 0. But now, you see, if you look at the second group of equation, additionally you have rho and J. So how to deal with that? Well, you can calculate that, and it turns out that this is equal to. Let me write down the result. So that is equal to 1 over C times the contraction of a vector field on the volume form. So the left-hand side is already clear. So let me explain the right-hand side. So there is a volume form which is omega, and that is defined as dx0 wedge dx1 wedge dx2 wedge dx3, and that's a 4-form. So that's a 4-form on our space, and it picks up an orientation. Now, what is J? So J is defined as rho ddt plus so our electric current is a 3 vector. It has 3 components. So I write down the 3 components in a differential geometric way. So it has 3 components, but this is this first part can also be regarded as J0 ddx0 where J0 is defined as C rho. So, so this is the statement. So we have the right-hand side is a contraction of a 4 form with a vector field, so it's a 3 form, whereas left-hand side is a D of a 2 form. That's also a 3 form. And you can check by explicit calculation that they are indeed equivalent. So, now, then there's something that you already know from undergraduate physics, that the Maxwell's equations are designed to imply the conservation of electric charges. And let's see how this works in the language of differential geometry. So, so let's make a remark that the second group of Maxwell's equations actually implies the conservation of charges. You can easily see this in the standard language of vector calculus, which you already see in physics. But let's do it in a differential geometric way. So, so let's see how this goes. Now, you see that D something is equal to the right-hand side. So, so that means D of the right-hand side is equal to at least, well, maybe a constant times D square of star F, and that is 0, because D square is 0. Okay, so once you see that, you have that the Lie derivative of J of the volume form is equal to 0, because the Lie derivative is D contraction plus contraction D on omega. The first term is 0 because of Maxwell's equation. The second term is 0 because volume form is already a top form, so it has no further D. So that is 0. So whenever a volume form is conserved along a flow, in this case a flow of J, then that means that J is a conserved vector field. So that alone implies that dj0 dx0 plus dj1 dx1 plus etc. Is equal to 0, and that's exactly the conservation law. Okay. Now, I don't want to make the impression that upon using Maxwell's equation, then everything is mathematical. In fact, there's still some physics considerations that we have to make. One is that we have electromagnetic field, but how do we know we have them? Now, so we have to answer the question how to detect concretely, how to detect E and B. And once we have E and B, then we can construct a two-form, etc. Right? So, but first of all, how do we realize that in this world we have E and B? Well, of course, maybe in high school, you know that we have to put test particles in the space, and then if the test particle is charged, so it's subject to a force, then that force divided by the charge is the electric field. Provided we assume that the dependence is linear and electric field is thus defined. So there is a force we can observe. Suppose the notion of force makes sense. How do we do that? Well, in Newtonian mechanics, we can look at accelerations, and then we realize that there is a force. So, so the force is equal to Q times E, where Q is the electric charge of a test particle, and force is force that is exerted on the particle that cannot be explained other than we have electric field. Now, how do we detect magnetic field? Well, essentially, in high school, we know that if we have a small segment of electric current, then it feels another force, and that if we orient our electric current in an appropriate direction, then we know the magnetic field. But equivalently, we can say that we put the particle in motion. The same particle, if it at rest, we already know the electric field. Now let it move, then it's subject to an additional force. Now it moves with velocity v, and in Gauss unit we need to divide it by c so that to make it dimensionless. And then the magnetic field is detected in this way. Of course, if you have only one velocity, it doesn't fix the magnetic field. But if you test with all possible v's, then you can know v uniquely. So this is how we detect electromagnetic field. Now, so this is one question: is how do we know that we already have them? Now, the second question is, it's mathematically very nice, of course. We summarized the Maxwell's equations into two very simple, very short formulas. One is this, and the other is dF is equal to 0. Right? Now, there's still a question. Now, we have a two-form on the four-dimensional space. In this four-dimensional space, we have already chosen coordinates. How do we know that this two-form is independent of our choice of coordinate? Maybe they depend on our choice of coordinate, and then this two-form is not so useful, although it summarizes nicely mathematical equations. So how do we know that the two-form is independent of our choice of coordinate? Then there are two issues. The one is the coordinate in 3 dimensions. So suppose, obviously they are given by a choice of orthonormal frame, but if we rotate the orthonormal frame, everything seems to be rotationally invariant. The isomorphisms in the diagram that are erased is invariant under SL3 rotation. So that doesn't matter. But what about the mixing of time and space? Now, in physics, there's a very special way to mix the time and space. That is given by special relativity. So, special relativity, you have Lorentz transformation. So these are called Lorentz boosts. Now, under a Lorentz boost, so we suppose we jump on a train, and it's in a uniform motion with the relative to the previous coordinate system. And then what happens is that according to special relativity, of course, V, in this test particle, V and F transform. According to the law of of special relativity. And so you actually know, so from one reference frame, if you jump on a train, before you jump, you can already calculate by special relativity how the velocity of the test particle would be on the train, and what the force is, because there's also a transformation law for the force. So that means before you jump on the train, you already know when you jump on the train, you'll see a different E and B, right? Because this V is arbitrary. So therefore the E and B also transform in a fixed way. You already know there's no way to say differently. There's already an answer to it. And so does F, because F is sort of mathematically constructed from E and B. So you already know that. Now, it turns out that under this transformation, F transforms according to precisely the mathematical rule of a two-tensor antisymmetric tensor. Now, I want to say that this is completely not automatic. You could have started with some physical rules to calculate how things would transform, and it wouldn't get you the mathematically how a two-tensor would transform. That is completely a possibility. But it turns out that this is the case. So F does transform according to the how a two-tensor how a two-tensor transforms under a coordinate change. Coordinate change means mixing x0 with x1, 2, and 3, and thus F is independent of the choice of space-time coordinates. So now we can mix sort of x0 and x1, 2, 3, and regard this as a coordinate of one coherent space. So this is the Minkowski space-time. So this I'm not going to do the exercise. The exercise is clearly defined, and you can do that yourself by referring to standard textbooks in special relativity. Now, the second thing, so this is one aspect of physics that we should not forget after seeing the mathematical formulation. And the other aspect of physics that we should mention is that you see, so E and B they form an F, which is a two-form. I don't want to specify the space. So this is a two-form, and the question is, so does this two form completely describe classical electromagnetism? So is it a complete description of the sort of situation or configuration of electromagnetism? Then we know that if you look at complex line bundles with connections, you find out that the curvature F is mathematically denoted by the same notation F. This is because in physics, this is a traditional notation. That's why in mathematics, it's also, the curvature is also denoted by F. And the curvature of a line bundle satisfies the equation dF is equal to 0. That is completely of geometric origin. That's the Bianchi identity. Now, it is wonderful if, let's say, our electric and magnetic field not only define a two-form on our space-time, but that two-form is actually the curvature of a line bundle. Right? Then half of the Maxwell's equations is automatic because our statement that this F is the curvature of a line bundle. And the other half is hello. Yeah. The other the second group of equation is dynamical, and it has no immediate relation with geometry. So, but we cannot make arbitrary sort of assumptions in physics without specific evidence, right? Now, indeed, Maxwell's equation says that this F is a closed two-form. But from claiming that F is a closed two-form, which has a solid physics basis, to claiming that F is actually the curvature of a line bundle, this is another jump, which may or may not be true in the real world. So if we want it to be true, we have to provide evidence. So it's not subject to us to say arbitrarily what our universe is or is not. We have to provide with evidence. So what kind of evidence can we provide if we want to claim that F that we constructed earlier is indeed a curvature of a line bundle, of a connection on a line bundle? Now, so we have to, in order to address that question, we have to say that we have to first of all realize mathematically what's the difference of a mere two-form with the curvature of a line bundle. So mathematically there should be some differences of the two concepts, and then we can say that in physics we do some experiments, and then our experience actually tells us that it's better the case that F is the curvature instead of just a two-form, right? So let's first look at mathematically what is more that we want to say about the curvature of a line bundle. Obviously, the curvature of a line bundle is a closed two-form, but what else? Well, then that comes back to the concept of connection on the complex line bundle. So, once we have a connection on a complex line bundle, then we can sort of, you have on every point in space-time, you have a complex line, and then you can parallel transport the various vectors in the complex line along a curve. And one thing is that if you parallel transport along a closed loop, then when you return to the original point in the space-time, the phase, there might be a phase difference in the complex vector in this one-dimensional space when you go around, say in the fiber. So this phase in the fiber is called holonomy. Now, this, so if we can manage to see if we manage to see the holonomy, then we can. That is an evidence of the claim that classical electromagnetism actually defines the F, and that F is actually a curvature. It's not just merely a two-form. So that is one sort of difference of, so one additional thing that we have when we have a connection of a line bundle. And the other thing is that the integrality condition. So we know that in the line bundle you have a curvature, and curvature, if you make this particular linear combination, that is a closed form, right? And that represents a class in the second Durand cohomology group. That element actually comes from the integer cohomology group. So that's the first Chern class of the line bundle. So if you do that, then you integrate this two form on any closed surface, closed embedded surface. It should be an integer. So in other words, there's some kind of privation phenomena, if you can observe in physics, that is related to the first Chern class being an integer. Then there is additional evidence. So this two-form F that are constructed from E and B is actually the curvature of a line bundle, just a closed two-form. See these two directions. And I'm now going to indicate that in both aspects, we can provide experimental evidence to show that these has to come from experiment. It cannot be deduced mathematically because this is additional statement on our physical world. So, we'll give evidence about the holonomy and the organization of integration of this two form, and that should be sufficient for us to believe that F is actually the curvature of a connection on a line bundle. Okay, so how do we do that? Well, first about holonomy. So holonomy, the corresponding experiment is, I'm sure you have heard it in physics. So it's a Haronov-Bohm effect. So first of all, when we look at information about holonomy, we know that certainly if the curvature of a line bundle is non-zero, then there is certainly holonomy. But if we find the case that the curvature of a line bundle is zero, and in that region we still have a holonomy, that means we have detected the effect of flat connection. Now, once we detected the effect of flat connection, then it shows that F itself as a two-form is not everything. There is an additional information, which is holonomy, that is related to connection. So this is how we should proceed. So, we have we start with we start with some with some very basic things in quantum mechanics, which is the double slit experiment. And that is, so we have an electron beam, and then there's some obstruction here with two holes, and then finally there's a screen. So that is sort of in popular science for quantum mechanics, you'll see this kind of experiment. So if you, even if you emit the electron one by one, then it will sort of go through these holes, which I don't want to describe. And then on the screen, you will find interference. So there's a big peak here, and there's smaller peaks. Okay? So this is because the electron has to be observed here. It hits the screen, and then it activates some photoenergetic material, so make it exposed to the energy. And then because the electron passes either through, well, I don't want to say that, but the electron passes through this, and there are phases arriving at this point is different for these two paths. And therefore, if you think about the wave-like behavior of matter, even if electron is a particle, sometimes behave like a wave, then there's an interference. Okay. So this has nothing to do with electromagnetism. And let's redo the experiment. Let's redo the experiment with a difference. So here there's some region which we single out, and then we put a magnetic field here, which point out of the blackboard. So there is magnetic field point out the blackboard, and we arrange the situation carefully so that there's no electric or magnetic field whatsoever outside this small region. And in this way, you see, originally, the electron cannot enter this region anyway because we already obstructed this part. Right? Classically, electron can either go through this hole or that hole. But now it's the same region, except that we put a magnetic field here. Now, in the region that the electron can reach, there's no change of the region, and there's no change of the electromagnetic field. So if the electromagnetic field defines an F, and if F is the curvature of some line bundle, then in the region where the electron can reach, that connection is flat. It has zero curvature because E and B are zero there. Now, if F is indeed a curvature, then we should be able to see physically the effect of traveling in a flat connection. Namely, flat connection can have holonomy along loops which are non-trivial in the fundamental group, right? So we should see physically the effect, and the effect is indeed seen in experiment. That is called the Aharonov-Born effect. The effect is that the interference actually is the same, but it's shifted a little bit. So the same pattern, there's a shift. And this shift means that the phase traveling from here and there is slightly shifted. And that is the evidence that even in the region of flat connection, we still affect, there's still physical effect on the outside world, which has some interaction with the electromagnetic field. So that means electromagnetism is not just two-fold. It is this shift is due to the holonomy. It's indeed coming from the holonomy of a connection on a complex line bundle. So what is the more concretely the relation between, let's say, the electromagnetic field and connection of a line bundle? So for that, we can look at let's say, we look at the Schrödinger operator. In a Schrödinger operator of a charged particle in an electromagnetic field, you see that the momentum is there's a square of momentum, but the momentum is shifted. Usually the momentum is minus psi h bar ddx, or that's the gradient nabla. But when we have, let's say, a magnetic field, then there's an additional term which is charge divided by c, and then there is a vector potential square. The vector potential is that defined as follows: since B has divergence 0, then locally it is the curl of another vector field A, and that A appears here. So, that operator, if you rewrite it, you can rewrite it as minus h bar. And then you have the nabla, the gradient operator, and then you plus q divided by I h bar c a. Now, here, the natural interpretation is that this is a covariant derivative. So, in other words, once we want to interpret electromagnetic field, namely this F, curvature of a line bundle, there is a line bundle, and the wave function in quantum mechanics is now not just a complex valued function, and this is the covariant derivative on the section of that line bundle. So, with this interpretation, then of course, if the electron traveling along two different paths, there's an additional phase difference due to parallel transport in a non-trivial flat connection, right? So there's an additional phase which can explain this shift in the experiment, and this identification of the operator as covariant derivative makes us to identify what is A in mathematics and what is A in physics. In physics, A is defined in this way. In mathematics, A is when we write down a connection locally, there's a one form A. So what are the relations between two? Now, in mathematics, this is the A. So our A in mathematics is equal to, that A is from physics, because I copied this from physics textbook. So it's A, this in physics. So when we want to make mathematical computation, we should use this translation. And we want to, when we have done mathematics, we want to translate it back into physics, we should also use this formula. And therefore, the F that I constructed was also from physics. So the F, which is a curvature, which is the curvature line bundle in math, is also given by the same formula. So because in physics you also see, in math you see F, and they're related in this way. And usually, as a sort of experimental fact, so this is Q is the electric charge is also quantized, and so this Q is actually an integer multiple of E, where minus E is the charge of the electron. So that means there's the most fundamental line bundle, and all the other line bundles. So there's a fundamental line bundle whose sections are wave functions of positrons, and all other line bundles are tensor powers of this line bundle according to what the integer is. So that's one evidence about the claim that this F is actually the curvature of a line bundle. In fact, F is not precisely the curvature, but after this factor, it is the curvature. Now, the other thing is about quantization. So the other thing is about quantization of. So when we look at the RAM cohomology, and when we say that it's the integral, we want to integrate it over a closed surface. So if all those numbers are integers, then it's an evidence that this is indeed a curvature. And so the integration of F in physics is called of flux, because it's obviously integration of a surface. It's something through the surface, so it's called a flux. So what about that evidence? So the integration of curvature along something is always sort of an integer. Now this is a bit hard because in our actual physical world, if you have a closed surface, then there's no hole at least in our usual laboratory setting. There's no hole in the middle, so the surface will shrink to zero, and by Stokes' theorem, the flux will be zero. But how do we do that? Nevertheless, to find a setting to test the quantization of fluxes. Well, we look at our material. So the usual conductor is something that inside E is equal to zero. So once there's E, that will immediately redistribute the electric charge to make it zero. Now, what about superconductor? Superconductor inside, not only E is zero, but also B is equal to zero. So B is equal to zero. That is called the Meissner effect. And both E and B equal to zero, that means our F is equal to zero. So in the superconductor, F is equal to zero. So the connection is flat. So then we look at a super conducting solid torus. So suppose our temperature is sufficiently low, then this is a solid torus inside the materials. superconducting materials. So inside this material, suppose we have a connection, then the connection is flat. And not only is the connection flat, the connection, our connection is actually trivial, namely, there's not even a holonomy. Why? Because, let's say, by the standard theory of superconductor, electrons form pairs called Cooper pairs. And then there is a field which describes the density of these Cooper pairs. Now this field turns out to be it's a kind of mean field. These are actually sections of so there is a standard line bundle corresponding to E, but Cooper pair is of charge -2, so it's tensor -2. So even if the original line bundle might be non-trivial, now we have inside the superconducting material, the density of Cooper pair is non-zero. So there is a global section of this line bundle. Namely, if we ignore the two, essentially I'm saying that not only is the connection flat, but the line bundle responsible for that is trivial, including the connection. So if that is the case, then if we put some magnetic field through the hole inside the torus, now this magnetic field, so let's say we have a circle here inside the torus, and mathematically the circle bounds a surface D. So this magnetic field integrated through this D. So this is the flux here. Now this flux is actually up to a factor. Sort of measures the relative first Chern class. Why relative? Because the boundary is trivial on C, but inside C, on D, it is non-trivial. So there's a relative second cohomology here, and mathematically you can compute that the second cohomology is isomorphic to Z. So the curvature, integration of the curvature here should represent an integer class here, and therefore this quantity is quantized. And experimentally, we indeed see, we only observe quantized experimental result of this magnetic flux. That gives another proof that electromagnetism F-constructed is not just the closed two-fold, but it's actually the curvature of line bundle. I think I'll stop